All right, so today what we're going to do is we're going to try to do lots of examples of groups and think about why they're groups. Make sure they satisfy the properties of group. And what you could do right now, actually, if you read ahead like I asked you to, is you could try to spend a few minutes trying to write down the definition of a group on your own here as part of participation credit. I'll get you started here. And in fact, I'll probably write as you go, but don't peek. You can peek right away to start here. A non-empty set G is a group if, okay, you keep going from there. And like I said, I will as well, but don't peek. This is our fundamental definition for the course, really, right here. And again, when you write definitions and theorems on exams, as I was telling people last week, since the exams are closed notes, closed book, part of your credit will be writing down definitions and theorem statements. I'm not looking for word, I'm looking for the right meaning. So while you can memorize, and that's okay, it's more important to understand. And this could be written in a few different ways. I'm going to write it slightly different than the book does. Try to get your quantifiers right as well. There exists and for all. If you want, you can peek. See if you can finish up in 30 seconds if you're not peeking. I was a little extra fancy here in the first sentence. if I were going to say this quickly, or if you were going to say this quickly without being too technical about it, maybe you're talking to somebody who's in linear algebra class and is just learning about vector spaces, and you're trying to use words that they should have heard about vector spaces. Doesn't quite match this, but what kind of things could you say a group is if you had to say it quickly without being super precise about it? I'm looking for really 4 things here. A group has an operation defined on it that satisfies what 4 things? And don't be misled by the fact that there's 3 things here. Closure, associativity, identity, and inverses, yeah. That would be a non-precise way of describing this quickly. This is the 4 key things that you want for a group. As I emphasize a lot in the lectures, binary operation implies closure. According to our author, not everybody does that, but this implies closure. Because binary operations are really functions, and we're saying the codomain of this function is the set G. If the codomain was something other than G, then it would not satisfy closure. In general, you might say a binary operation is just a way of combining 2 things to get 1 thing. Binary, 2 things to get 1 thing. G cross G, if you've never seen this before, that's called the Cartesian product of G with itself. As a set, it's just a set of all ordered pairs of elements whose coordinates, if you like, or components are from G itself. So you might say the set of all ordered pairs A comma B such that A and B are in G. Whatever G happens to be, that collection of ordered pairs, whether you're thinking about it as G as being a finite group or an infinite group, or trying to imagine graphing this or something and thinking of this as a plane, well, you can't always think of it as a plane. That's called the Cartesian product. And when we say that the group operation is a binary operation, we are saying, technically speaking, is a function like this that takes an ordered pair and maps it to an element that we call AB. We put A next to B, but we imagine that as A times B. We don't typically put the dot in there, though you could. There's nothing wrong with putting the dot in there. We just get lazy, and we don't. However, we hardly ever write the ordered pair, right? We usually just write the product. The ordered pair, in a sense, is just understood, but this is just, to be technical about it, that's technically what it is. An ordered pair gets mapped to AB, which is some element of G. This is an element of G, which is emphasized by the fact that the codomain of this function is G itself. Division, you might say, is a binary operation, as taking 2 things and giving you 1 thing, you know, taking the integers 1 and 2 and giving you 1/2. But it's not a binary operation according to this, at least not on the set of, say, the set of integers, even if you take out 0, so you avoid dividing by 0, because you could get a non-integer from division. So in a sense, it's a binary operation, but not according to this definition. And yeah, associativity. ABC equals ABC, where it doesn't matter where you put the parentheses. This would emphasize to do AB first, then multiply by C. This would emphasize to do BC first, then multiply on the left by A. I should have said multiply on the right by C. Where you multiply, on the left or the right, matters. It's just like matrix multiplication. It matters. Commutative property does not hold in general. Here there exists an identity element, typically called E, because again, it's historical origins were German. Z stands for Zahlen in German. E stands for Einheit, I believe, which kind of means identity, I guess. One, you might say. Sometimes people just call this a one. They write the number one there, though that doesn't necessarily represent the number one. Exists in E such that AE equals EA equals A for all A and G. That's identity. And here's your existence of inverses. And you get the quantifiers right. For all A and G, there's an inverse. There's an A inverse suggestively written like this. You don't have to write it like that if you don't want to be suggestive at first. You can just call it B or something. So that A times that element in either order gives you the identity. Some fundamental basic consequences of this definition. Essentially, we take these as axioms when we do group theory. All groups, when you do the theory, are assumed to satisfy these. Though in practice, when you try to work with a particular group, you have to verify that these are true right away in order for it to be a group. Does that make sense? When you do the theory, you take these as axioms, you might say. All groups are assumed to satisfy these. When you apply the theory to particular situations, you have to check in that situation, are these axioms satisfied? And we will check that today. And in particular, you do have to check closure. You do have to check that this operation, however you're defining it, is truly a binary operation in this sense that the codomain is G itself as well. That has to be checked. So yeah, existence of inverses. And yes, what are those basic consequences? Some basic consequences of this definition. That can be proved. I do prove in the lectures. The book proves as well that, for example, the identity is unique. There can only be one such element that satisfies this property right here. One such element E. The argument to prove it is pretty quick, but maybe slightly tricky. You got to realize what you need to do. Second consequence is, well, inverses are unique, but I think before that, it's easier to prove something called the cancellation law. Or maybe I should say cancellation laws. There's a left cancellation law and there's a right cancellation law. The left cancellation law says that if A times B equals A times C, you can cancel the A's on the left and get B must be equal to C. You've done that kind of thing with matrix algebra before. If you pretend these things are matrices, what would you do to verify that? Assume that's true. What would you multiply by on the left to verify this? Yeah, the inverse of A, or an inverse of A if you don't yet know the inverses are unique. And that's what the same thing you do with group theory here. You don't need to pretend they're matrices. You've got the tools you need. And on the right cancellation law is, say, BA equals CA. That also implies B equals C. But if the A is, say, on the left side, well, on the left side of the equation, on the right side of the equation, you can't cancel the A. Warning, this is not a theorem that I'm writing down, it's a warning. AB equals CA does not necessarily in general imply B equals C. They could be equal, but not necessarily. If the operation happens to be commutative, if it's what's called an abelian group, then that would be true. But in general, you cannot assume that the group is abelian. You cannot assume that the operation is commutative. Why? Why not assume it? Because you don't need to. There are plenty of groups that are not commutative, like matrix groups, where the operation is multiplication. And we want those to be groups. Those are interesting enough that we want to include them in groups. If we want to consider groups that are commutative, abelian, then we go ahead and say, well, let's assume we've got an abelian group. And the third basic consequence I already mentioned is that inverses are unique. And the easiest way to prove that is with the cancellation law. So, or one of the cancellation, both of them, I guess you could say, if we're thinking about left and right inverses, although we do assume here that our inverses are both left and right, that A and its inverse commute. But we can prove the inverses are unique as well. Can I clarify anything there? Any questions? All right, let's have you work on some examples now. I'll start you with a couple examples, and then you can work. And for those who came in late, part of your participation credit is going to ultimately be taking pictures of your work and uploading it to confirm that you worked on it. But we can do some real basic examples first. If I define G to be a one-element set and just say call that element E, and I define a binary operation on this set by mapping the ordered pair E comma E to E itself, that's the only binary operation that can be done, you might say. That's the only, it's a function that maps one thing to itself, or not to itself, but this thing to this thing. That's a group. And it's got a Cayley table that's very simple. Now, what is a Cayley table? I said it's a generalization of a multiplication table. You put the group elements along the column there and along the row there, if it's a finite group at least. And then you multiply and you put the answer in this part of the chart. E times E is E. Done. Is it associative? Yeah, it's trivial to check. E is definitely E is E, which is also the same as E, which is the same as E. What fun. There's an identity. E is identity. And there for each element, there's an inverse. E is its own inverse. You could write the equation E inverse equals E. And in fact, that's always true in any group. The identity element is its own inverse. Okay, let's up the level of complication a little bit. How about a two-element group? Well, let's take a particular two-element group. Why don't we take Z2 under addition mod 2? Now the Cayley table we should really think of it as the operation of addition, right? Not multiplication. Addition mod 2, maybe I could have put a plus sub 2 there. I have to add and then mod by 2. 0 plus 0 is 0 mod 2. 0 plus 1 is 1 mod 2. Starting on the left here and then going to the top. 1 plus 0 is 1 mod 2. And 1 plus 1 is what? 0 mod 2. There we go, done. Is it a group? It's a binary operation. For example, the ordered pair 1 comma 1 gets mapped to 0. Your mapping is always either to 0 or 1. It's to an element of G. It is associative. Should we check that? We usually don't bother. It is. Okay. You can check it. I'm not going to bother. Is there identity? I don't see any E's in here. Yes, you're right. 0 is the identity. The operation is addition, not multiplication. And does each element have an inverse? Yep. 0 is its own inverse, and 1 is its own inverse. Because the operation is addition, however, we would not write 1 to the negative power, negative 1 power. You shouldn't necessarily always think of it as negative 1 power, though informally you do when you write that kind of thing. It's not the same as division, so you got to be a little careful. But when the group operation is addition, instead of writing to a power, you write the negative sign in front. It's an additive inverse instead of a multiplicative inverse. So you'd say negative 1 equals 1. Yes, that's true, mod 2. The additive inverse of 1 is itself. The additive inverse of 1 is itself. I mean, and it is also true, you could also say, based on modding that we talked about last time, negative 1 mod 2 does equal 1, and that also equals 1 mod 2. Right? When you divide negative 1 by 2, you do get a remainder of 1. Why? Because according to the division algorithm, you should think of negative 1 as being 2 times negative 1 plus 1, where the remainder is between 0 and what you're dividing by, 2. I'm modding by 2. You should not think of it as 2 plus 0 plus negative 1. I mean, that is true, but that doesn't fit the division algorithm. We want a remainder to be non-negative and less than what we're dividing by, between 0 and n minus 1 inclusive. N is 2 here. And that's true as well. When you divide 1 by 2, you get a remainder of 1, because then you'd write it this way. You don't need to write that stuff all the time, by the way. Just add multiples of 2 to get what you want. You remember reading about congruence mod n as well? I haven't really emphasized that in class. A is congruent to B mod n. Notice the 3 lines. That's an equivalence relation. That's defined by saying n divides B minus A, or A minus B, whichever way you want to think about it. That's the definition of congruence mod n, which is an equivalence relation. And you can informally think of these equations as being congruencies as well. Something is going to be equivalent to something else mod n if you can get from one to the other by adding or subtracting multiples of n. In this case, n is 2. I can get from negative 1 to 1 by adding 2, a multiple of 2. All right, why don't you take some time now to fill in the Cayley table for Z3. Addition mod 3, whose elements are 0, 1, and 2, and identify the inverse of each element, the additive inverse. Make your Cayley table. You work on that right now. So we're not really doing general things here. We're doing particular examples, though we can point to general things. Notice that these Zn groups are abelian. 1 plus 2 does equal 2 plus 1, no matter what you're modding by. In this case, those are equal to 0 mod 3. You can think of this part down here as being a matrix if you like. And as long as the elements of the group are in the same order along the column over here as they are along the top row up here, when this matrix is a symmetric matrix, it equals its transpose. When these elements across the main diagonal are the same, that's equivalent to being abelian. Right? 1 plus 2 is the element that goes there. 1 plus 2 is there. 2 plus 1 is there. Start on the left over here and go up to the right. 2 plus 1, they meet down there. Those are the same. It's abelian. Yeah, these Zn groups are abelian no matter what n is. Yes, you can write the additive inverse of 0 is itself. 0 is the identity. The additive inverse of 1 is 2. Additive inverse of 2 is 1. And these are 3 apart, mod 3. These are equivalent mod 3. They're congruent mod 3. You could say all those things. You might wonder, okay, that's a particular example of a group with 3 elements. You might wonder if you could sort of write down an abstract example of a group with 3 elements. Could you? Could you just say, let G be E, say A, B. Maybe let the operation be some sort of multiplication. And make a Cayley table in the abstract. Could you do that? Not really saying what these things are. Not saying they're matrices, not saying they're numbers, not saying they're functions. They're just symbols. And suggestively, we're thinking of E maybe as being the identity. If that's going to be the case, I guess you could fill in these things. Could you fill in these other 4 spots to make this a group? A group that's purely abstract. No concrete thing that we're necessarily referring to here. Could you do this? Could you decide what A times A should be? And what A times B should be, and B times A, and B times B? Well, you could try to match the pattern up here, for one thing. And I guess it would have to be a group if you do that, wouldn't it? Because it would have to match the pattern that you see. I guess A is corresponding to 1. And up here, 1 plus 1 was 2. Down here, if A is corresponding to 1 and B is corresponding to 2, I guess this better be A times A is B. And 0 corresponds to E. So I guess I better make A times B equal to E. And I fill the rest in and I'd get this. Is that okay to do? Turns out, yes, you can do that. You can define an abstract group, a purely abstract group with 3 elements, define the multiplication in the analogous way we did up here, and yes, it would be a group. Doesn't have any meaning besides just being an example, but it is a group. Are these choices, however, unique? Could I have picked different things in these 4 spots? And then have it be a group. Evidently, the red spots have to be the way they are if E is going to be the identity, right? They'd have to be that way. But what about these 4 spots? Could I have picked some different order? Could A times itself be A, for example? Is it possible that I could have put an A there? Well, no, not if E, A, and B are all distinct, because the cancellation law would then imply A equals E. Left cancellation law. I'm going to go ahead and put slashes through these, but that's not necessarily a good idea. Cancellation. Okay, I won't mark it wrong if you do, but people generally avoid doing that. That would be a contradiction because I'm assuming EA and B are all distinct. So I can't put A there. Could I put E there? Well, we have seen elements, non-identity elements that are their own inverses. Going back up here in Z2, for example, 1 is its own inverse. It's not the identity under addition mod 2. Could I put it? Let's just give it a try and see what happens. E, A, B. So I'm going to make another Cayley table where I need to keep the red ones the same because E I'm taking to be the identity. What would happen if I put an E here? Would I be in trouble? Then A would be its own inverse. B has to have an inverse as well. I guess inverses are unique. I guess the inverse of B would have to be E itself as well. What do I put here and here, though? There's a problem either way. I do it. If I say take here, whether I choose A or B, there's a problem. A question mark, B question mark. If you choose it to be A to go there, then you'd be saying B times A is A. And the cancellation law would imply B equals E. Because you could write this as EA. And that would be a contradiction. If you put a B there, then you'd be saying B times A equals B. And the cancellation law would imply A equals E, and that's a contradiction as well. If you think of this as B times E. Either way you do it, that's a contradiction. So what I'm trying to say is, this is the unique group of order 3 in the abstract. It does match this group of order 3 as an abstract, just how the tables match up, so to speak. These are what I call isomorphic groups. This one is defined via a specific set and specific operation. This set under addition mod 3. This group and this defined with this Cayley table is purely abstract. The EA and B are just distinct symbols. I define the multiplication tables, the Cayley tables, so that these, that's why it's better to say Cayley tables because this is not really a multiplication table. I define the Cayley tables to make these match. And it turns out for groups with 3 elements, we call those groups of order 3, no other thing you try will work. The groups of order 3 with 3 elements are unique up to isomorphism, we say. Groups of order 2 are unique up to isomorphism as well. Groups of order 1 are unique up to isomorphism as well. Does that continue? What about groups of order 4? Well, let's have you try an example first. Fill in the Cayley table for this one. Z4, 0, 1, 2, 3, under addition mod 4. You might want to make the lines that separate the group elements from the main body of the Cayley table with bolder lines. you get this? So that's Z4. And it's abelian. Is that the only possible group of order 4 up to isomorphism? Well, I'm going to show you another important example of a group, what you might call a U group. And I'm going to consider what's called U8. This is something you read about if you read chapter 2. This is called the group of units under multiplication mod 8. What does it consist of as a set? As a set, it's the collection of positive integers that are relatively primed 8. Less than 8 and relatively primed 8. Say that again. This is the set of positive integers less than 8 that are also relatively primed 8. Now 8's not a prime, but there are numbers less than 8 that are relatively primed 8. 1, for example. What's another example of a number less than 8 but positive that's still relatively primed 8? 3. 5 and 7, which are all primes. In general, the numbers that you're looking at don't have to be primes. For example, if we were talking about, say, what would be a good example? U14. What are the numbers less than 14 that are relatively primed to 14? They do include non-prime numbers, right? For example, is that right? 9, yeah. Thanks. 9 is less than 14 and is not a prime, but is relatively prime to 14. Let's look at what the Cayley table for this one looks like. Careful, so the operation up here was addition mod 4 plus sub 4. Now we're going to do multiplication sub 4. I'm making the plus sub 4 and the minus sub, the dot sub 4 for emphasis. In general, you don't have to bother. What's the identity in this group? What's the identity element? 1, yep. 1 times anything is that anything. So you can fill that in quick. I guess we'll work on this together. What's 3 times 3 mod 8? 1. 3 is its own inverse. 5 times 5 mod 8. 5 times 5 is 25. Mod 8 is 1. 5 is its own inverse. 7 times 7 mod 8. 49 mod 8. 7 is its own inverse. Right away, by just looking and seeing that each element is its own inverse, we see that these two groups are not isomorphic. I forgot to write down the additive inverses up here. The additive inverse of 0 was 0. The additive inverse of 1 was 3. The additive inverse of 2 is itself. The additive inverse of 3 is 1. So this group with 4 elements has 2 elements that are their own inverses, 0 and 2. But this group with 4 elements, and it will be a group, we'll finish the table here in a second, has all 4 elements of their own inverses, and you should use the power notation here because it's a multiplication. All 4 elements are their own multiplicative inverses. These groups, just because of that, they can't be isomorphic. The structure of these tables is going to be different. I'll quickly fill in the rest here. 3 times 5 is 15. 15 mod 8 is 7. Right? 15 mod 8 is 7. 3 times 7 is 21. 21 mod 8 is 5. This is an abelian group. You're going to get 7 and 5 down there. Oh, oops. Yeah. Then 7 times 5 is 35. 35 mod 8 is 3. And there's no way you can rearrange the order of these elements on this table here to make the pattern match this table. It's not possible because, for one thing, because of this, because every element is its own inverse in this group, whereas that's not true in this one. There's no way you'd be able to rearrange it to match the same structure. So we have at least two groups of order 4 that are not isomorphic. Are there any more? Turns out there's not. And you could do sort of an abstract argument with Cayley tables again, with an abstract situation to argue for why there's no more than 2 groups of order 4 up to isomorphism. It's a trickier argument. I'm not going to bother. But that is something you can take to the bank. Up to isomorphism, there are only 2 groups of order 4. Doesn't mean there's only 2 ways to represent group of order 4. There could be lots of different ways of representing a particular group of order 4. I mean, the elements could be numbers. They could be, well, these numbers, they could, do you know they could be complex numbers? I guess we will do a little bit with complex numbers here. The set G consisting of the numbers 1, -1, I, and -I, where I is the so-called imaginary unit, the square root of -1, turns out to be a group of order 4. Under what? Do you think it's addition or multiplication? It'd have to be under multiplication because, for example, 1 plus I doesn't equal any of these. Yeah, it's a group under multiplication, and 1 is the identity. Let's quickly make the Cayley table. One is the identity, multiplicative identity. -1 times itself is 1. It's its own inverse. I times I is -I. I squared is -1, excuse me. -1, not +1. I is not its own inverse. Neither is -I. -I times itself. It turns out the rule is you would get rid of that negative sign because you would think of this as -1 squared times I squared. And in effect, we're assuming it's commutative, but that's based on the definition of complex multiplication to begin with, so we can trust that. This gives you -1. Fill in the rest here. -1 times I is -I. -1 times -I is +I. Same kind of thing here. It is an abelian group. I times -I is +1. And that's the same as -I times I. Yeah, 1 is its own inverse. -1 is its own inverse. I is not its own inverse. Its inverse is -I. Same with -I. It's not its own inverse. Its inverse is I. Is this a new group up to isomorphism of order 4? Well, based on what I said a few minutes ago, it can't be. Which one is it isomorphic to? Which one does it have the same form as, Z4 or U8? It's got to be, thinking about the inverses, which one? Stop me. Say stop when I should stop. Be brave. Thinking about the number of elements who are their own inverses, it's got to be top one. Boom. It's got to be the same form as that. Isomorphic. Now, that can be a little confusing here because you see -1 times -1 gives you +1. Confirming -1 is its own inverse right there. You see 1 right there, the identity. Whereas you don't see the identity 0 right there. In the same spot of the table, you might say. Well, that's just because you need to rearrange the table, that's all. If I rearrange this table and put, say, I after 1, say in this order, then the tables would match up the pattern. And you could check it. For example, here you get I times I was -1, not the identity. Here in this spot right there, you get -1 times -1, 1, which is the identity, which matches the fact that you have a 0 right here. So you just need it in a different order is all. Now those tables would match up the pattern. Here's something else worth pointing out with these examples. In this group here, every element is actually a power of I. I to the first gives you I. I squared, I times I gives you -1. I cubed is I times I squared, is I times -1 is -I. And I to the fourth power is I cubed times I is -1 times I is I. Excuse me. What did I do wrong? -I times I, which is +1. Every element is a power of I. I mean, you could even think about it as 0th power as giving you 1 as well. If you define an element to the 0 power to be the identity, which we actually do in a multiplicative group like this. And how does that work out with this one that it's isomorphic to? Well, remember, it's not, the operation here is addition, not multiplication. So instead of doing powers, we do multiples. 1 is 1. 2 times 1, which you should think of as 1 plus 1, is 2. 3 times 1, which you think of 1 as 1 plus 1 plus 1, is 3. And 4 times 1, which you can think of as 1 plus 1 plus 1 plus 1, is 0. Every element is a multiple, you might say, of 1. That doesn't happen with this group. Take any of these elements and raise to bunch of different powers, and you're not going to get the whole group. Because of the fact that when you square any of these elements, you get back to the identity. So 3 squared, for example, is 1. So 3 cubed is 3. 5 cubed is 5. 7 cubed is 7. That's another fundamental distinction between these groups. Groups where every element is a power in the abstract of a group element are called cyclic groups. And they are the simplest kinds of groups. They're the main subject of chapter 4. Can I clarify anything there? Okay, let's end class today by thinking about symmetry groups. As you read about in chapter 1, symmetries of an equilateral triangle, symmetries of a square, symmetries of a regular pentagon, etc. However, I'm going to put a little twist on it. I'm actually not going to think of them as symmetry groups, but groups that permute corners of, say, a triangle. When you draw the triangle and you're thinking of it truly as being a symmetry group, it should be an equilateral triangle. So you read about what are the symmetries of this based on what reading in chapter 1. There are rotations. For example, you could rotate counterclockwise by 120 degrees and it would look the same. You could rotate counterclockwise by 240 degrees and it would look the same. You could not rotate at all and it would look the same. Of course, you could do other rotations, rotate by negative 120 degrees, though that has the same net effect as rotating by positive 240 degrees. You can also reflect. It's got lines of symmetry. For example, across this line, if you reflect across that line, it looks the same. Across this line, if you reflect across that one, it looks the same. And across this line, straight up and down, it would look the same. Those are called reflections or flips for short. They are also symmetries of this as functions of points in the plane, which you could write down formulas for actually. If you, for example, pretend it's easiest to pretend the origin is right in the middle of the equilateral triangle, to write down formulas for those. Actually, it'd be simpler to assume the origin's at the bottom of the triangle, in the midpoint of the bottom line segment. That would be simpler. You could write down formulas for those functions, and the operation is composition. Make sure you understand that as you read chapter 1, as you reread it, or read it for the first time if you're behind in your reading. However, since the main thing that matters is where the vertices end up after those rotations or flips, you may as well just think of it as a function on the vertices and maybe give the vertices names. Maybe even call them numbers. How about 1, 2, 3? Which one you pick to be 1, which one you pick to be 2, which one you pick to be 3 is arbitrary. I guess I kind of did a weird way there. It might have made more sense to do 1 up here, 2 over here, 3 over there. Okay, doesn't matter though. It's just a labeling. If I'm thinking about like clock arithmetic or something, that might have made more sense. I was thinking more about counterclockwise rotations as being a positive rotation. That's why I did it that way. You could just think about it as functions on this 3-element set. The 1, the 2, and the 3 are just labels for the vertices. I could have used letters A, B, and C. Though when you talk about permuting these, changing their order, it is traditional actually to use numbers. Though they don't really represent numbers in the usual sense. They really just represent convenient symbols, labels. What do I mean by permuting? Well, for example, if I rotate by 120 degrees, so here I am literally thinking of a rotation here. Yeah, I can redraw the triangle, and it looks the same. But really the more important thing is what happens to the labels. The 1 gets rotated up here, the 2 down here, and the 3 is here. As a function on the 3-element set, this is equivalent to 1 getting mapped to 2. The 1 here in the lower right corner gets mapped to the location up here in the top that 2 was originally in. That's why 1 gets mapped to 2. 2 gets rotated down to here, the spot the 3 was in to begin with. 2, in effect, gets mapped to 3. And 3 over here gets mapped to the lower right corner where 1 was originally. So you think of that as 3 getting mapped to 1. It gets mapped to the spot that 1 was in originally. That's a function on just a 3-element set. It's called a permutation. Permutation in general is just a reordering of things. We learned about permutations in probability and statistics and maybe discrete math. Just a reordering. It's really a one-to-one and onto function from a finite set to itself, typically is the way you think about it. Maybe we shouldn't call it R120 anymore, because if we're just thinking of this being this function on this 3-element set, it's not really a rotation anymore. It's a function. It's traditional to use a Greek letter. I'm going to give the 3-element set a name. I'm going to call it I want to avoid a certain letter, a certain couple letters. I'll call it C3. But that's just kind of an arbitrary letter to use. Alpha maps C3 to itself. It's a one-to-one and onto function. It maps 1 to 2. It maps 2 to 3. And it maps 3 to 1. Alpha of 1 equals 2. Alpha of 2 equals 3. Alpha of 3 equals 1. But that's not the only permutation. It doesn't correspond. It corresponds to one particular geometric transformation. That's a symmetry. There are others. Rotating by 240 degrees, maybe I should call that alpha squared. Because to rotate by 240 degrees, you could think of it as first rotate by 120 and then by another 120. Alpha squared from C3 to itself. What does it map 1 to? Well, thinking of the rotation back up here, 1 would eventually get mapped to 3 under a 240-degree rotation. 2 is going to get mapped to 1 spot. And 3 is going to get mapped to 2 spot. And am I really squaring something? I mean, am I not composing functions? The answer is yes and yes. Maybe I should say emphasize the composition first. I am composing functions here. Alpha squared is alpha composed with itself. R240 is R120 composed with itself. And it's squaring, not in the usual sense of squaring, because I'm not literally multiplying in the usual sense, but I'm multiplying in an abstracted sense, in a group theory sense. It is a group operation. And you could confirm, if you think of it as a function composition, alpha squared of 1 is alpha of 1. Alpha of 1 we know to be 2. This is alpha of 2, which is 3, which confirms that. And you can do it with the other ones too. What about flips? What about reflections? If I rotate about a line like this, 1 and 2 are going to get swapped and 3 stays where it is. If beta maps from C3 to itself, by swapping 1 and 2, but leaving 3 fixed, that is a permutation. That's a reordering, so to speak, of the vertices or of the numbers. What happens if I square that permutation? If I compose it with itself, I'm going to get the identity permutation. Beta squared equals E. Well, maybe since we're using Greek letters, we should use the Greek version of E, epsilon. Beta squared of every one of these numbers is itself. It's the identity permutation that leaves all numbers fixed. That corresponds to rotating by 0 degrees, or say not flipping at all. What about the other flips? How about the other lines? Should I give those new Greek letter names? You could, but you don't need to. Turns out that alpha beta, alpha composed beta will be a new permutation. What's alpha beta of 1, for example? It would be alpha of beta of 1, which would be alpha of 2, which is 3, going back up, looking back up here. Alpha of 2 is 3. What's alpha beta of 2? Alpha of beta of 2. Beta of 2 was 1. So this is alpha of 1. That will equal 2, looking back up here. Alpha of 1 is 2. And alpha beta of 3 is alpha of beta of 3. Beta of 3 was 3 itself. That's yet a new permutation that's not, we haven't written down yet. And there's one more. Alpha squared times beta. Alpha squared beta of 1. But what's alpha squared? Well, beta of 1 is, again, 2. What's alpha squared of 2? It was this, 1. Right back up there. Alpha squared beta of 2 is alpha squared of beta of 2. Beta of 2 is 1. Alpha squared of 1 turns out to be 3. And finally, alpha squared beta of 3. Beta of 3 is 3. Alpha squared of 3, excuse me, is 2. This is a 2 here. And that's yet another permutation. And this exhausts the possibilities. There's 6 permutations here. Alpha is 1. Alpha squared is a second one. Beta is a third one. Beta squared, which is epsilon, is a fourth. The identity permutation that maps these numbers to themselves. Fifth, a 6th element. These are 6-element group here, ultimately. And it turns out to be not commutative, not abelian. Let's maybe check that on Wednesday. Okay, that's it.